Welcome to Gnanataranga program. This program is organized by Department of Pre-University Education, Government of Karnataka. Myself, Dr. Laksmikantha. I am from Vidya Mandir Independent PU College, Malleshwaram, Bangalore. In this class, we are going to discuss about the synopsis followed by the NEET CET questions on current electricity topic. So, first begin with the synopsis of electric current. Electric current. Electric current flow of charges constitute electric current. For steady flow of charges, I is equal to Q by T. If the rate of flow of charges varies with time, then we are going to take I is equal to dQ by dt. The SI unit of current is ampere and it is a scalar quantity. See here, current has both magnitude and direction. And the current to magnitude helbodu 2 ampere, flowing direction ತೋರಿಸಬಹುದು, but still it is a scalar quantity. ಯಾಕೆ? It does not obey the vector addition rule, so that it belongs to scalar quantity. See 1 ampere, how you are going to define the 1 ampere? 1 ampere which is equivalent to 1 coulomb per second. The conventional direction, how you are going to take the conventional direction current? The direction of motion of positive charges is taken as the direction of conventional current. Next, current density. See, it is the amount of charge flowing per unit area normal to the flow of the charges. The direction of current density is in the direction of the motion of the positive charges. Normal flow of the charges J is equal to I by A, means current per unit area. In general, we are going to say taken as I is equal to J A cos theta, that is J A vector J dot A. Suppose I am given the one diagram. In this diagram, the area of cross section of different position is different, but through the wire the current remains the same. Okay. The SI unit of current density is ampere per meter square and it belongs to a vector quantity. Drift velocity. The average velocity acquired by the free electron of the conductor in the opposite direction of the externally applied electric field is called as a drift velocity. It is given by Vd is equal to EE divided by tau divided by m into tau, where E is the charge of electron, E is the electric field, m is the mass of the electron, tau is the relaxation time. The order of the drift velocity is about 10 raised to minus 4 meter per second. Then we know that what is the relaxation time? The average time that elapsed between the two successive collision of the electron is called as a relaxation time. It means that the electron take the time collide with the next electron, the time interval between them is equal to relaxation time tau. So that is it is of the order of 10 raised to minus 14 second. Next, relation between the drift velocity and current. We have I is equal to NEA into Vd, where N is the charge of the electron, E is the charge of the electron, N is the number density of the electron, A is the area of cross section, Vd is the drift velocity. And also we can write J is equal to I by A, current per unit area. If you substitute the value of I in this equation, we get J is equal to NENVD. So next we will pass on to the mobility of the charge carriers. Mobility of the charge carriers is the drift velocity acquired per unit electric field, that is mu E is equal to Vd divided by Ed. In different forms we can write mobility also. The SI unit of mobility is meter square per volt per second. Ohm's law. According to the Ohm's law, the current flowing through a conductor which is directly proportional to the potential difference between the conductor, provided temperature and other physical condition remains constant, that is V proportional to I, or we can write V is equal to I, or R is equal to V by I. The proportionality constant in the equation we referred as a resistance of a conductor. See, Ohm's law we can also write in the vector form, that is J vector is equal to sigma into vector E. Okay, or else if you write in terms of electric field, E vector is equal to rho into J vector. Resistance. It is the opposition offered by the conductor to the flow of the current in a conductor. It is also defined as ratio of the potential difference across the conductor to the current to the conductor, that is VR is equal to V by A. This resistance depends on so many factors. Say for example, resistance it is directly proportional to the length. Similarly, resistance directly proportional, inversely proportional to the area, and this is also directly proportional to the temperature. Okay, this is also depends on the nature of the material. On these four factors, the resistance of a conductor depends. The SI unit of resistance is ohm. The definition of 1 ohm is equal to 1 volt per ampere. The reciprocal of resistance we referred as a conductance, that is G is equal to 1 by R, that is the reciprocal of the resistance. The SI unit is per ohm or Siemens. These are the two units used for the measurement of the conductance. Next, see some devices which obeys the Ohm's law, say for example resistor. Okay, resistor which obeys the Ohm's law, such devices we referred as a ohmic devices. If you plot a graph, this is the potential versus current. Okay, if you plot a graph, we get a linear curve. Such devices we referred as a ohmic devices. Some of the devices like PN junction diode, this is you can consider this is V by I, you can take this is the current and this is the voltage. We get a curve like this, non-linear curve. Such devices we referred as a non-ohmic device. Next we move on to the color code for the resistors. See, we have metallic resistor, other different types of resistor, but we are using the carbon composition resistor. In carbon composition resistor, we are not supposed to get the values directly. By taking the help of the color band on the surface of the resistor, we can calculate the value of the resistor. Before that, one must know the list of the color followed by the numbers. Here we are presenting the color, number and the multiplier we are given. See, that is black, brown, red, orange, yellow, green, blue, violet, grey, white. See, black 0, brown 1, red 2, orange 3, yellow 4, green 5 and blue is 6, violet is 7, grey is 8 and white is 9. Followed by the multiplier, as usually the power, whatever the number is there, no, they are going to rise to the 10 power. Okay, here in the left side of this diagram I am given the which type of the resistor is given, and on that diagram I am given the followed by A, B, C, D 4 bands. In the first band indicates the first significant digit, and the second band indicates the second significant digit, and the third band indicates the 10 power, and the fourth band indicates the tolerance band. Okay, in the fourth band only we have only two colors, one is gold. If it is gold, you are going to take the tolerance band or error band plus or minus 5%. If it is silver, then you are going to take the plus or minus 10%. If the fourth band is absent, no fourth band, only we have a 3 bands, then you are going to consider the error is 20%, that is plus or minus 20%. How you remember this list of the colors? So, we are going to have a one sentence for that one, that is B.B. Roy of Great Britain had a very good wife. This is the sentence to remember all the colors in this. Okay, the first color is black 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, grey 8, white 9. Like that, we remember this color. We can easily calculate the color code for any resistor. Next, temperature coefficient of a resistance of a conductor. Okay, it is defined as the change in the resistance per virginal length per unit rise in the temperature. That is the variation of the resistance with temperature is given by the equation RT is equal to R naught 1 plus alpha T. Rearrange that equation, we get alpha is equal to RT minus R naught whole divided by R naught into 3. That is alpha is nothing but increase in resistance or change in resistance divided by resistance at 0 degree into the unit rise in the temperature, which give rise to alpha. That alpha value can be mentioned in the SI unit of the alpha is per degree Celsius or Kelvin. Suppose if you have a variation of the resistance with the temperature graph like this. This is the resistance and this is the temperature in degree Celsius like this. We have a graph like this. They were providing the value of the 2 points like this. This is the resistance R1, this is the resistance R2, followed by the temperature T1, and this is equal to T2. In these 4 parameters, using these 4 parameters, we can easily calculate the value of the alpha like this. Okay. So this is the lower value of the resistance, this is the higher value of the resistance, because here temperature is more, then resistance is also more. By using this, we can calculate the alpha value. effect of temperature on the resistor, effect of temperature on resistance. Okay, say for example, we are going to consider metals, alloys and semiconductors. Okay, in case of alloys, okay, we can consider in case of metals, we have a variation of the resistivity or temperature, whatever it may be, resistivity with temperature, we get a curve like this. It means that if you vary the temperature, resistance also increases. Similarly, in case of alloys also, we have the same parameter, that is temperature T, we get a curve like this. It is also temperature increases, resistance also increases, but here the variation of resistance is very small. In case of semiconductor, we can explain that. So this is the resistance and this is the temperature. When temperature increases, resistance decreases. This is inversely, and these two are directly. This is combination of resistors. Combination of resistors means we have two combination. One is series, another one is parallel. First we know that the combination of resistors is series combination. Here in this diagram I am taken the three resistors R1, R2, R3. They were connected to end. The common point is connected to the source of voltage V. The effective resistance of for this particular diagram, Rs is equal to R1 plus R2 plus RT. If they were providing only two resistors, then the equation can be written as Rs is equal to R1 plus R2. Okay, if the resistor consists of n number of resistors, then you followed by this equation. Suppose in case we have all the resistors, this like n number of resistor equal to R, then the equivalent resistance is NR. Similarly, the voltage across this is equal to this and this. How you are going to calculate? The total voltage, whatever we given this voltage, no, that is the voltage across individual, that is V dash, is equal to V divided by N. Suppose you are connecting 3 resistor, 3, the total voltage is 12. 12 divided by 3, which gives rise to 4 volts each. Means equally voltage is divided when equal resistors are connected. Similarly for parallel combination. In parallel combination, here in this diagram I am taken the 3 resistors, they were connected to 2 common points, and the common point is connected to source. Okay, the equivalent resistance is equal to 1 by Rp. Rp means parallel, that is equal to 1 by R1 plus 1 by R2 plus 1 by R2. Okay, this is for 3 resistors. If you have only 2 resistors, then in this case you are going to have Rp is equal to 1 by R1 plus 1 by R2. Okay, like this we are going to use. If it consists of n number of resistors, then the formula 1 by Rp is equal to 1 by R1 up to 1 by Rn terms. Okay, if suppose all the resistors equal R, like n number of resistors are connected in parallel, then the effective resistance is equal to R by N. Suppose you are considering 2 ohm resistors, the 10 are connected in parallel. So the value of the resistor is 2. How many numbers? 10. If you divide by 2 by 10, which gives rise to 0.2 ohm, that is the effective resistance. Similarly, in this case, for all the resistor, potential across this is equal to same. The current will divides. The current in each resistor we can calculate. I dash means each resistor is equal to I divided by N. This is applicable only all the resistors are equal. Division of current in a resistor joining in a parallel. See, if you have only 2 resistors, how you are going to calculate the I1 and I2 values? By using the formula I1 is equal to R2 divided by R1 plus R2 into I. Similarly, if you want to calculate I2 is equal to R1 I divided by R1 plus R2. This is called branch current formula. It is easily find out the current in the circuits. Yes. Suppose next I will move on to the concept is called as a stretching of the wire. See, stretching of the wire means if you have a wire like this, okay, by applying some other thermal heat treatment, whatever it may be, it is going to expand like this. Okay, expand like this. This is the original wire, this is the expanded wire. Okay, if you are going to expand, the resistance changes. Why resistance changes? The resistance is directly proportional to the length and inversely proportional to the area. When we stretch the wire, length increases, area decreases, obviously resistance increases. So therefore, they were given in terms of number of times or in terms of percentage. Therefore, here I am going to add 4 different methods to the stretching. The first one, if the wire resistance R is stretched to n times its original length, its resistance becomes n square R. If you stretch by n times, then the new resistance is equal to n square R. Okay. Say for example, this is equal to R, then the new resistance R dash is equal to n square R, like this. New resistance means R dash is equal to n square R. Okay. Say for example, this wire having the resistance of 2 ohm. What is the resistance in this? It is expanded to 3 times. Therefore, R dash is equal to how many times? 3 times. Original resistance is 2. 3 square is 9. 9 into 2 is equal to 18 ohm. Like that you are going to calculate. The second one is, they were going to in terms of radius. If the wire of the resistance R is stretched till its radius becoming 1 by n of its original radius, then its new resistance becoming n to the power of 4 into R. N power 4 into R when it is stretches by in terms of radius. Similarly, they were given in terms of percentage. When a wire is stretched to increase its length by x%, length is x%, then the resistance increases by 2x%. Similarly, they were given in terms of radius. When a wire is stretched to reduce its radius by x%, its resistance increases by 4%, like this. This is the concept related to the stretching of the wire. We can easily solve by taking the help of these 4 parameters, like this. Suppose using n conductors of equal resistance, the number of possible combination is, we have this equation, that is 2 power n minus 1, where n is the number of resistors. Say for example, they were given the 5 resistors of equal values. Okay, 5 resistors they were given. How many combination in series, parallel combination you are going to form? So number of formations, number of combination is equal to 10 power 5 minus 1, which is equal to 2 power 4, multiply by 2 into 2 into 2 into 2, 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 combination we can obtain. Okay, in this way we are going to obtain. The second one, if the n resistors conductors are totally different, then the combination is possible. If they were not identical, the resistors are not identical, then the formula is equal to 2n. Okay, n identical resistors are first connected in series, then connected in parallel, then the effective resistance is given by, say for example, when equal resistors are connected in series is equal to nr. In case of parallel, R by n. Okay, if you take the ratio of these two, okay, the ratio of these two, that is Rp divided by Rs. Rp is R by n into Rs is like this. Okay, it can this is Rp R by n, and this is, you can calculate cancel these two, we get Rp divided by Rs is equal to 1 by n square, or in other terms. Yes, if the wire R is cut into n equal parts and then these parts are connected in the form of a bundle, it means that parallel combination, then the resistance of the combination will be, okay, we are getting that R divided by n square. If the equivalent resistance R1 and R2 in series, the parallel, series and parallel be Rs and Rp, they respectively, then the resistances of R1 and R2 we can calculate by using these two formulas. This is for R1, this is for R2. Next, this is the one most important problems. Okay, it requires lot of step to calculate, but here we am given the very shortcut to calculate the. This is a skeleton of a cube. All the sides of this skeleton having the resistance which is equal to R. Now I would like to calculate the resistance between the longest diagonal. The longest diagonal in this problem I would like to consider this is A and this is equal to G. The resistance between A and G, which is given by 5 by R, 5 divided by 6 into R. Similarly for face diagonal means you are going to have A and F. This is equal to R by 3 into R. We are going to calculate the any one side, that is AB, resistance between A and B, which is equal to 7 divided by 12 R. Yes, electrical energy. Electrical energy means it is dissipated in the form of a heat, which is given by H is equal to PT, P power T time interval. Power can be written as voltage into current into T. It is expressed in joule. Suppose the value expressed in terms of current, it can be written as I square R into T in terms of joule. In terms of voltage, V square T divided by R. See, power of rating. Power rating, okay, in bulbs they were going to give the rating, that is 60 watt 220 volt bulb, that is called as a power of rating. In such cases we are going to calculate the power of the rating bulb. Power is equal to V square divided by it is in terms of current, I square divided by I square into R, both voltage and current, that is equal to P is equal to VI. Power consumed by a series combination of the bulb. Here, when bulbs are connected in series, there are two different bulbs of equal voltage. Okay, two different bulbs, 60 watt 220 volts, 40 watt 220 volts. Okay, where there are two bulbs are connected in series for the supply. So, we are going to calculate the power of this combination for series combination. 1 by P is equal to 1 by P1 plus 1 by P2 plus 1 by P3, like this. Okay, this is the total power calculated for the series combination. Okay, see, if the powers are identical, this is 40 watt, this is 40 watt, then we are going to calculate the total power is equal to P divided by N. See, for series combination, the power consumed, it means that which is the going to glow the brighter, directly proportional to the voltage, directly proportional to the resistance, and inversely proportional to the P rated. P rated means whatever the rated layer written on the bulb. Okay, suppose we have 40 and 60, we have 40 is the lowest watt. According to this relation, the lower watt bulb, okay, lower watt bulb which glow more brighter because it is inversely proportional. Okay, similarly here I am given the in wordings, the bulb which is lesser wattage will glow brighter and the potential across it will be a more. Here the voltage is also more. Similarly, for parallel combination of the bulbs, okay, the total effective combination, that is total power combination is equal to P1 P2 plus P3. If the all bulbs having the equal voltage, then we have P total is equal to NP. For this, power consumed is equal to directly proportional to the current, directly proportional to the P rated, inversely proportional to the R. It means that when bulbs are connected in parallel, which is having the greater wattage will go brighter. Yes, next we will move on to the next concept is called as a cell. A cell is a device which converts chemical energy into electrical energy, is known as a electric cell. A cell is a source for the constant supply. Why? What is the meaning of the constant supply? See, we are taking the connection for the home mode applications. They were given the connection. That is given the voltage is fluctuating. Some of the experiment we require the constant flow of the voltage. In such cases, we need this type of cells. Throughout the experiment, they supply the constant EMF. Therefore, more favorably, so many experiments they need a cells. Here I am going to give a picture of a symbol of the cell, which consists of the electrode. One is positive electrode, another one is the negative electrode, which are connected to the external resistance R. Okay, this is the circuit symbol of the cell, and this is the diagram for the derivation purpose. Okay, see here what is an EMF? The potential difference across the terminals of the cell when circuit is open. See, here we have a key. Okay, this is open. This is open. If you measure the potential difference across the terminals of the cell, then it is becoming a EMF of the cell. EMF of the cell can also be defined as the amount of work done to transfer a 1 coulomb of charge one terminal to the another terminals of the circuit. This is also called as a EMF. Yes, next, terminal potential difference. Simply we call it as a terminal potential difference. The potential difference across the terminals of the cell when cell is closed. Cell is closed. If the cell is closed, now we are going to measure the potential difference across the cell, then we refer as a terminal potential difference. Internal resistance. Here in this cell we have a solution and these are the electrode. In this electrolyte solutions ions are there. These ions are exchanging between the anode and cathode. While exchanging the ions, the solution which opposes the motion of the ions. Thus the opposition offered by the electrolyte through the flow of the ions in a cell we referred as a internal resistance of a cell. This internal resistance of a cell depends on the 5 parameters. Number 1 is nature of the electrode, concentration of the electrode, distance between the electrodes, and area of the electrode and temperature of the electrode. Because of all these points, the internal resistance depends. The relation between the EMF, terminal potential and internal resistance. This is for the equation given E is equal to V plus IR. This is for discharging the cell. This can be written as like this, rearranging this equation, terminal potential is equal to E minus IR, where E is the terminal potential difference, E is the EMF of the cell, minus I is the current and R is the internal resistance. By taking the help of the Ohm's law, we can write V is equal to IR. We know the value of I, substitute the value, we get ER divided by R plus R is the terminal potential difference. See, suppose when the current is maximum in the circuit, we are going to consider that these two are equal. It means that the external resistance should be equal to the internal resistance when the current is maximum. Okay, that is we can write I maximum is equal to E divided by R for short circuits. Yes, terminal potential difference of the charging. So this is I was explained the charging. Now it is discharging. Now it is charging. See, we are going to do the charging the cell. Now it is becoming V is equal to E plus IR. In this case, V is greater than E. A cell is said to be an ideal if has a zero internal resistance. Now power dissipated in the external this thing, we are going to have a P is equal to Vi. In terms of I square R. In terms of voltage, V square by R. So we know the value of the expression for the I, that is E divided by R plus R, power R into R. Okay, the power delivered will be maximum when this is R is equal to capital R is equal to small r. It means that external resistance is equal to the sum of the internal resistance of the cell. Then the power dissipated is maximum. P maximum is equal to E square divided by 4R. If you plot a power versus resistance curve, we get a curve like this. Next, cells in series and cells in parallel. The equivalent EMF of the combination, the EMF is equal to, when n number of identical cells, we have equivalent EMF is equal to NE. When equivalent internal resistance is equal to NR, the current in the circuit is equal to I is equal to NE divided by R plus NR. If the potential difference across the resistance is equal to V is equal to IR. Potential difference across each cell is equal to V dash is equal to V by N. The power dissipated is equal to that is I square R. This is the value of the I. The condition for the maximum power is external resistance, which is equal to the sum of the internal resistance, that is R is equal to NR. Then power in the circuit is maximum, that is equal to N E square divided by 4R. Similarly, for parallel combination of the cells, when cells are connected in parallel, okay, the effective EMF is equal to E only in case of identical. Equivalent internal resistance is equal to R by N for parallel combination. Then current in the circuit is equal to this much. The potential difference across the external resistance is equal to V is equal to IR, because we know the value of the I. Similarly, the current from each cell, we are going to calculate I dash is equal to I by N only for identical. Similarly, power dissipated in this case is equal to, this is I square R, that is E divided by R plus R, R divided by N into all to the power of 2 into R. See, condition for the maximum power is equal to external resistance should be is equal to R by N, and the power maximum is equal to N E square 4R. Next, mixed group. It consists of parallel as well as the series mixed group. So n number of cells are connected in series, m number of rows are connected in parallel. The total cells in this circuit is equal to m into n. The equivalent EMF for the mixing of the cells is equal to Ne, equivalent internal resistance is equal to Nr by m, and the total current in the circuit is equal to Mne divided by Mr plus Nr. Current in the circuit is, voltage in the external resistance is equal to IR, voltage in each branch is equal to V divided by N, current is equal to I dash is equal to I divided by N. Similarly, for the maximum power is nothing but the this value R should be is equal to the sum of the internal value. So that is R is equal to Nr divided by M, then the power is maximum. The total number of cells in this combination is equal to M into N. Next we will move on to the Kirchoff laws. According to it, the algebraic sum of the current meeting at a junction is 0. In mathematically, we can write sigma I equivalent to is equal to 0. In the diagram given, sum of the current is entering to the node. I am taken as O. Number of current is entering the towards the junction, and sum of the current is leaving the junction. But the algebraic sum of the current at this junction should be is equal to 0. That is the meaning of the sigma I. See, the convention for the taking the current in sign convention is entering the current taken as positive, leaving the current taken as negative. Sum of the entering current is equal to sum of the current leaving the node. That is also the statement for the Kirchoff's first law. It is also called as a current law. The law simply the statement of the conservation of charge. It is very, very important. Okay, charge neither be created nor be destroyed. On that principle, this law is a consequence. Next, I will move on to the Kirchoff's second law. The algebraic sum of the EMFs and changes in the potential around any closed loop in an electrical network is 0. That is sigma I plus sigma IR is equal to 0. This is the algebraic sum of the EMFs. This is the algebraic sum of the potential. The sum of these two, which is equal to 0. This is the consequence for the law of conservation of energy. First law is consequence of charge. Second law is consequence of energy. Yes, the sign convention for taking the IR product, whether it is a plus or minus. If you are moved from A to B in the direction of the current, we are going to take IR product is minus IR. Suppose you are moving from B to A, then the IR product is taken as positive, plus IR. Means direction, in the direction of the current, we are going to take minus. Opposite to the direction of the current, we taken as a plus. Similarly, in case of the EMF, when we move from higher potential to lower potential, the EMF is minus E. If you move from lower potential to higher potential, then the EMF is positive. This is the sign convention. If you know this sign convention, it is easy to solve the Kirchoff laws problems. It is very easily. Yes. Now we will move on to the very important concept, that is called as a Wheatstone's bridge or Wheatstone network. This Wheatstone bridge consists of 4 arms, P, Q, R, S. These forms are connected in the form of a quadrilateral, A, B, C, D, quadrilateral. The side A and C, which is connected to the source of EMF or a battery, and the terminals B and D connected to the galvanometer. This is the diagram. Okay, see, we are going to interchange the values of the PQR such that the current through the galvanometer is 0. That is nothing but the balancing condition of the galvanometer. In balancing condition, the potential at B and potential at D should be the same. It means that the potential at B and potential at D should be the same. The potential difference is 0. Once the potential difference is 0, no current will flow in the galvanometer. It means that the value of the galvanometer resistance does not depends on this current flowing. Okay, it is independent. Even though you are changing the value of the galvanometer, say for example in the first case 50 ohm. After the balancing, you are going to change of 100 ohm. No alter takes place in the Wheatstone's bridge. Similarly, after balancing condition means you must know that P by Q is equal to R by S. Okay, if you interchange galvanometer and the battery, okay, means galvanometer is connected between AC and battery is connected between BD, no change in the balancing condition, no change in the balancing condition. And also I give the one idea, all the forms of the resistors, all the 4 arms of the resistor is equal. Say for example X, 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 all are equal. The net resistance of this is equal to, that is R net, total resistance is equal to X only. This is very important for calculating the answers. Next, here I am given the what I am discussed, the configuration of the adjacent figure is called as a Wheatstone's bridge. If Ig is equal to 0, that is galvanometer current is 0, then the bridge is said to be balanced. For Ig 0, Vd and Vb are equal, potential at D and potential at B equal. In that condition, P by Q is equal to R by S. To calculate the equivalent resistance bar balancing condition, that is P plus Q R plus S divided by P plus Q plus R plus S, that is the equivalent resistance. Suppose the bridge is not balanced, the bridge is not balanced. See, this is the value of Q, this is the value of the S. If you multiply by these two, one thing, and multiply by these two, the second thing, you observe this. If QS greater than PR, then VB greater than VD, the current will flow from B to D. The second one is, if QS is less than PR, then VB less than VD, then the current flow from D to B. It is very important. No need to calculate the entire thing, only you observe these values, whether it is greater or lesser. By taking the help of this concept, we can easily calculate the current is flowing in which direction. Yes. Next we will move on to the applications of the Wheatstone's network. The first application of this one is meter bridge. I think the students were very familiar with the Wheatstone bridge. In laboratory we are using this meter bridge. Okay. This meter bridge is an instrument which is used to find out the resistance of the unknown wire. Okay. We are going to find out the resistance of the wire. And this is working on the principle of the balancing Wheatstone network, not Wheatstone network, balancing Wheatstone network. Okay. See, in balancing Wheatstone network, for this particular diagram, we can have S is equal to 100 minus L divided by L into R, or else you can calculate X is equal to SL divided by 100 minus L. If you want, calculate the value of the X. This is usually in practical you are measuring X, and this is they were taken the S value, standard resistance, and this is the value of the X, unknown resistance. Okay. By help of this you can calculate the easily. X is equal to SL divided by 100 minus L, means you are measuring the distance, balancing length in terms of centimeter, it is holds good. If suppose you are measuring the balancing length in terms of meter, this is equal to 1 minus L. This is in terms of length, in terms of meter. Yes. Potentiometer. A potentiometer is a device mainly used to measure the EMF of the cell and to compare the EMF of the cells. It is also used to measure the internal resistance of a cell. This is the diagram. In this diagram, we have primary circuit and the secondary circuit. Primary circuit is, that is as usual a meter bridge type, the potentiometer, which consists of a variable resistor, either rheostat, whatever it may be, and this is the source along with the key, and AB is the wire. AB is the wire. And this is the external circuit, consists of the cell with the galvanometer and the jockey. This is the secondary circuit. Now, to determine the internal resistance of the primary cell using this circuit diagram, okay, this is the primary circuit and this is the secondary circuit. So, by taking the help of R is equal to L1 minus L2 divided by L2 into this is R, that is external resistance is R. Okay, this is the value of the R. By taking the help of this, we can easily find out the internal resistance of the cell. Similarly, to compare the EMF of the two cells by using the potentiometer. Say for example, this is the arrangement of the potentiometer. Okay, first you are going to close the key 1, find out the balancing length, that is equal to L1. When E1 is closed, balancing length is L1. Remove the key first and place the key at the 2. Then measuring the measuring the balancing length, that is your L2. Take the ratio of these two, that is E1 by E2 is equal to L1 by L2, because E directly proportional to L, E is equal to some constant into L. This is a constant for a given potentiometer. Yes. See, if suppose they were given in place of this, they were given two cells are in series or two cells connected in wrong way, then we are going to have like this. These are the two cells, they were connected in series. We get the effective balancing length is equal to E1 plus E2 is equal to X means some constant into L1. Similarly, the EMF when they are connected wrongly connected, then E1 minus E2 is equal to X into L2. Take the ratio of these two. X is a constant, cancelled on each term, we get the equation, or else we can also write in this form. Okay. Now, let us begin with the questions. Electric current and current density are, your options are A, scalar quantity and vector quantity, B, both are scalar, C, vector quantity and scalar quantity, D, both are vector. So, in the synopsis only I have discussed. So, current is a scalar quantity, even though both magnitude and direction it is belongs to a scalar quantity. One is clear, current is a scalar, Next we will move on to the current density. Current density is a vector, it is in the direction of the motion of the positive charges. Therefore, the correct option is current is a scalar quantity and current density is a vector quantity. The correct answer for this question is A. Question number 2. Current flowing through a wire varies with the time t as I is equal to 2t plus 4 dash 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 ampere. How much charge passing through a cross section of the wire in 2 seconds? Option A 8 coulomb, option B 4 coulomb, option C 16 coulomb, option D 12 coulomb. See here we have a solution. See, we can write current is equal to dq divided by dt, Rearrange the expression, dq is equal to I into dt. So, integrate on both sides. Integration of dq is equal to q. So, integration from 0 to 2. Why I am taking 2 means we are going to calculate the 2 seconds from 0 to 2 seconds. Therefore, the limit is 0 to 2 seconds. The I value they were given in the problem, that is I is equal to 2t plus 4. That is I am substituting, that is equal to dt. Now, integration of 2t, that is 2t square divided by 2. Integration of 4t, limit is, upper limit is 2, lower limit is 0. If you apply the limits, here 2 and 2 gets cancelled, it is t square plus 4t, 2, 0, upper limit, lower limit. First I would like to upper limit, 2 square is 4 and 2 4s are 8. We get 4 plus 8 which is equivalent to 12 coulomb. Therefore, the correct answer for this question is equal to D. Question number 3. A copper conductor of increasing diameter is shown in the figure. Which of the following quantities vary along with the length of the conductors? Okay, here the diagram providing in this is variable cross-sectional area, Okay, see, we have the expression for current as well as current density, electric current and drift velocity like this. For current density, current per unit area, and in terms of current density in terms of electric field, J is equal to sigma E and I is equal to NEA VD, VD is equal to I divided by NEA. So, in this case, area goes on increasing because like this, area increases. If you move like this, area increases. If area increases, the current density decreases. Decreases. Okay, 1. Here, current density decreases, electric field decreases. Here, this is VD, drift velocity. Drift velocity and area inversely related. If area increases, this value decreases. So, therefore, all the 3 parameters like current density and electric field, drift velocity, all the 3 parameters varies, but current in a conductor remains the same. Therefore, the correct answer for this question is A, that is electric current. This is the correct answer. Question number 4. The relaxation time in the conductor, options A, increases with increase in temperature, decreases with the increase in temperature. It does not depend on the temperature. All of sudden changes as 400 degree Celsius. First we know the concept of the relaxation time. Already in the synopsis I have discussed, it is the time elapsed between the two successive collisions of the electrons. That is order of the 10 raised to minus 14 second. That is we have a relation. This is resistivity, which is equal to m divided by n e square tau. This resistivity and the relaxation time are inversely related. We have a graph, resistivity versus temperature. For conductors we have a like this, increases with increase in temperature. Okay, here this is relaxation time and resistivity inversely related. If resistivity increases, relaxation time decreases from this. As the temperature increases, the resistivity increases, and hence the relaxation time decreases in a conductor. Therefore, the correct option is B. This is the correct option. Question number 5. When current I is flowing through a conductor, the drift velocity is Vd. If 2I current is flowing through the same metal but have double the area of cross section, then the drift velocity will be option A Vd by 4, option B Vd by 2, option C Vd, option 4 4Vd. For the solution, we have an expression current is equal to NEA Vd. Rearrange this equation, we can write drift velocity is equal to I divided by NEA. See, after the change in area and the current, then the drift velocity is Vd. Vd dash is equal to, the current is double 2I, area is double 2A. This two cancel, the remaining is I divided by NAE. See, before that drift velocity is I divided by NAE, after the expansion and increasing the value of the current, I divided by NEA. So, therefore, Vd and V dash are the same, therefore Vd is equal to V dash. The correct option is C, therefore no change in the drift velocity. This is the correct option. In a current carrying metallic conductor, the current density J vector, electric field E vector and drift velocity Vd will be such that we are given the 4 different options. See, first option, J and V opposite direction and J and E in the same direction, first option. Second option, J and V same direction, J and E opposite direction. Option C, J and V have opposite direction and J and E opposite directions. Third option, J and V same direction, J and E will have the same directions. So, the answer for this is equal to, if you draw the conductor like this, here we are going to apply the potential. This is the higher potential and this is the lower potential. It consists of the free electron. Okay. When we apply the potential difference, the electric field is developed in the direction of the opposite to the motion of the electron, in this direction. This electron moving with the velocity Vd like this. The direction of the flow of the conventional current is in this direction, and I told you electron means negative charge, it is moving in this direction. Okay, definitely the positive charges is moving in this direction, therefore the density, current density is in this direction. Similarly, the area of this is also in the same direction. From this diagram we conclude that all the 3, electric field and the current density, area vector are all current are in the same direction, towards the negative direction. Only the drift velocity opposite to this. Therefore, the correct option for this is equal to A. It means that J and Vd will be opposite direction. Definitely Vd opposite to J, and the second, and J and E will be of the same direction. See, J and Vd in the opposite direction and E and J are in the same direction. Therefore, correct option is A. Question number 7. The drift velocity of the electron in a copper wire of length 2 meter under the application of the potential difference of 100 volt is 0.2 meter per second. Their mobility is in meter square per volt per second is option A 2.5 10 raised to minus 3, option B 2.5 10 raised to minus 2, option C 4 into 10 raised to minus 3, option D 4 into 10 raised to minus 2. The solution for this, so we have a relation, drift velocity is mobility is drift velocity per unit electric field. Okay, this can be rearranged, this the electric field can be written as V by L. So therefore L is shifted to up, Vd into L divided by V. Vd is the drift velocity, L is the length, V is the voltage. Substitute the values, that is Vd is 2 meter per second, length is 2 meter and the potential is 100 volts. 2 into 0.2 is equal to 0.4. This is 100. 100 can be written as 10 power 2. When it is go up, it is becoming minus 2. If you shift 4 to this side, it is becoming 10 power minus 3. Therefore, the correct answer for this question is C. This is the correct answer. Question number 8. The voltage V and current I graph for the conductor at two different temperatures T1 and T2 as shown in the figure. The relation between T1 and T2 is option A T1 is equal to T2, option B T2 greater than T2, option 3 means C T1 less than T2, option D T1 is equal to T2 by 2. See, from this graph we can calculate the slope of the line, that is slope, anywhere you can calculate, this is the slope of this. Okay, that slope of the line give rise to resistance of the material, the slope which is nothing but a tan theta, voltage by current which give rise to resistance. See, according to the tan theta value, if theta is more, then tan theta value is more. Therefore, from the diagram theta 1 is more, theta 2 is less. Therefore, tan theta 1 is greater than tan theta 2. Similarly, it is directly proportional to tan theta, R1 greater than R2. Similarly, one which is having the temperature is high, definitely resistance is also high. Therefore, T1 greater than T2. The correct option for this question is B. Question number 9. The length of the resistance wire is increases by 3%. What is the corresponding change in the resistance of the wire? Here the problem, the option number A 3%, option number B 6%, C 9%, D 12%. Already I have discussed the same problem in the synopsis. That is called stretching of the wire. Here they were going to increase the length by 3%. Say for example, X% of length is increases, its new resistance is increases by 2x times. By taking the help of that concept, we can easily solve this question. Okay, that is, when a wire is stretched to increase its length by X%, its new resistance will increases by 2%. Therefore, 2 into the original is 3%. 2 into 3 is equal to 6%. Therefore, the correct option for this is equal to B. Next. If a copper wire is stretched to make its radius, it decreases by 0.1%, then the percentage increase in the resistance is nearly. This concept is also same concept, that is based on the stretching of the wire in terms of radius, that is reduces the radius in the sense length increases, okay, means resistance increases. If X% of radius is reduced, the new resistance will increases by 4x%. Taking the help of that concept, we can easily calculate that one. Okay, so that is, when a wire is stretched to decrease its radius by x%, its resistance increases by 4%. 4 into 0.1% is the original. Therefore, 4 into 0.1 is equal to 0.4%. This is already I have discussed in a synopsis. This is the skeleton of the cube. The 12 wires of equal length and same cross-sectional area are connected in the form of a cube. If the resistance of each resistance of the wire is 6 ohm, then the effective resistance between A and G is option A 12 ohm, option B 6 ohm, option C 3 ohm, option D 5 ohm. See, I already discussed about the A and G from the diagram. This is a body diagonal. For body diagonal, the effective resistance between A and G, which is equal to 5 divided by R into R, 5 divided by 6 into R. Okay, they were given the value of the each arm, that is equal to 6. Therefore, 5 divided by R into multiply by the resistance value, that is 6. That is the solution. That is RAG is equal to 5 divided by R into R, where R is equal to 6 ohm. Okay, 5 by 6 into 6, 6 cancel, the effective resistance is equal to 5 ohm. If suppose they may ask phase diagonal, say for example, this is the phase diagonal. Okay, I will name them B, C, D, E, F, G, H. See, this is the phase diagonal, that is RFH. Okay, RFH, that is the phase diagonal. For that, resistance is equal to 3 by 4R. R is the resistance value. Similarly, if you want to calculate the resistance for the side, this is the side, that is RFG is equal to, we have a effective resistance 7 by 12R. Okay, this concept you can also use it for the other problems. Question number 12. The resistance of the wire is R. If the length and area of cross section of the wire are doubled, then the new resistance will be A, R by 2, B, 2R, C, R, D, R by 2. For this, we have a relation between length, area and resistivity. Resistance is directly proportional to length, inversely proportional to area, and rho is the resistivity of the material. So, the resistivity of the material does not depend on the dimension, it should be the rho only, no change in the value. So, therefore, this is before the value increase, that is R is equal to rho L by A. After increasing the length and area, we have R dash is equal to rho L dash by A. Length increases by 2 times, that is 2L, area increases by 2 times 2A. 2 gets cancelled, we get again rho L by A. See, this is the value of the R dash, this is the value of the R. This and this one and the same. Therefore, the correct answer for this question is equal to C, that is equal to R. Question number 13. In the figure, a carbon resistor has a band of different colors on its body as mentioned in the figure. The value of the resistance is option A 9.1 kilo ohm plus or minus 5%. Option B 1.1 kilo ohm plus or minus 10%. Option C 9.1 kilo ohm plus or minus 10%. Option D 1.1 kilo ohm plus or minus 5%. Okay. First you identify the two answer for this, means we are going to select any two easily, because first you see the fourth band. Which is the fourth band? Silver color is there. Okay, silver color we are going to error is equal to 10%. See, we are not supposed to take A and D, only we have 10% is B and C. Okay, over. So next, how you are going to define, how you are going to identify whether B is correct or C is correct. Okay, see, first color, which is the first color? White. White having the number 9. Correct, no? See, here 1 is there, here 9 is there. Therefore, the correct answer for this is equal to C. Or else we can also do by taking the help of the color code method. This is very easy method to identify. First and the last colors are there correctly. Okay, then the answer is correct. Okay, this is the way you are going to calculate the value of the resistor, that is by taking the help of B.B. Roy, Great Britain, very good wife. Okay, here the first color is white, white is having the 9, therefore I am taking the 9, first significant digit. The second color is brown, so brown they were taken 1, the second color, that is 91 over. The followed by the third band is red, red means we have value is 2, therefore 10 power 2. So, this is 10 power 2. So, this is white, this is brown and the value of 2 is red over, plus or minus silver, that is 10%. If you want to shift the value, okay, if you want to shift the value by placing a decimal point, it is becoming 10 power 3. Therefore, 9.1, 10 power 3 is nothing but kilo ohm plus or minus 10%. This is the correct answer. Therefore, C is the correct answer. A set of n identical resistors, each of resistance R ohm, when they are connected in series, has an effective resistance is equal to X. It means that RS they were taken as X. When the resistors are connected in parallel, the effective resistance is Y, that is Rp is equal to Y. What is the relation between R, X and Y? Option A, xy by x plus y. Option B, R is equal to y minus x. Option C, R is equal to root of xy. D, R is equal to y plus x. This is y. By option it is missing, y plus x. The solution for this, for series combination, RS, in place of RS they were taken x is equal to NR for identical. For parallel, RP is equal to R by N. Okay, you are multiply by x and y, you are getting NR into R by N. N gets cancelled, xy is equal to R square. We want value of the R, therefore R is equal to, this is equal to, R is equal to root of xy. Therefore, the correct option for this is equal to C. This is the correct option. Yes, question number 15. If each resistance in the figure is 9 ohm, then the reading of the ammeter is option A 5 ampere, option B 8 ampere, option C 2 ampere, option D 9 ampere. Okay, see all the resistors in the equation is 9 ohm, all are 9 ohm, 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 like this. All the resistors having the 9 ohm. They were connected in parallel. The net resistance Rp is equal to R divided by N. The value of R is equal to 9. How many resistors are there? That is equal to 9. The effective resistance is equal to 1 ohm over. Current is equal to V divided by R. Voltage by resistance. That is, voltage is 9, then resistance is 1. Therefore, this is equal to 9 ampere. 9 ampere means it flows a 9 ampere of current in the circuit. Okay, 9 ampere, because of the identical resistor, current will divide it equally. There are 9 resistors are there. Each resistor is equal to 1 ampere. 1 ampere current. So 1 ampere, 1 ampere, 1 ampere, 1 ampere, 1 ampere. Therefore, 1 ampere, 1, 1, 1, 1, 1. This is also 1, 1, 1, like this. This is 1 ampere, 2 ampere, 3 ampere, 4 ampere, 5 ampere. The 5 ampere of current flowing in this circuit. Therefore, the correct option is the reading of the ammeter is equal to 5 ampere. The correct option is equal to A. So, this is the total resistance R by N, that is total resistance is equal to 9 by 9 is equal to 1 ohm, current is equal to V by 9 by 1, that is equal to 9 ampere. Therefore, the current to the ammeter is equal to 5 ampere. Option number 16. A, B, C are the voltmeters of the resistance R, 1.5 R and 3 R respectively as shown in the figure. When some potential difference is applied between X and Y, the voltmeter readings are VA, VB and VC respectively. Then option A, VA not equal to VB not equal to VC. Option number B, VA is equal to VB is equal to VC. Option number C, VA not equal to VB is equal to VC. Option number D, VA is equal to VB not equal to VC. Okay. Here they were given the 3 voltmeters. This is the one, this is the second one and this is the third one. Okay. These two are connected in parallel. These two are connected in parallel. Okay. See, this value according to the problem, this value is 1.5 and this value according to the problem, this is equal to 3R. They are connected in parallel. Find out the effective resistance of this combination by taking the help of Rp is equal to R1 R2 divided by R1 plus R2. So, find out the value of the parallel resistance. Okay. So, this is the resistance, this is R1 and this is R2 and this is R1 plus R2. By made all the simplification, the value is equal to R. The total resistance of these two is equal to R over. And what is the value of A according to the problem? This is also equal to R. Here resistance are equal and connected in series, then the voltage across this and voltage across this combination should be the same. It means that the voltage across XZ should be equal to voltage across ZY, because resistances are equal, connected in series, connected in series, equal resistor, therefore voltage will divide equally, therefore that is Vx is equal to Vp, therefore the voltage across this, voltage across this, voltage across this should be the same, no change, therefore the correct option is B. Question number 17. A wire of resistance 12 ohm per meter. They were not given the entire resistance of the wire. They were given resistance per unit length. That is, a wire of resistance 12 ohm per meter is bent in the form of a complete circle of radius 10 centimeter. The resistance between its two diametrically opposite points A and B shown in the figure is A 0.65 ohm, B 3 ohm, C 6.5 ohm and D 6 ohm. See, they were not providing the total resistance of the wire. First we are going to calculate the total resistance of the wire, then we are going to divide the half circle. See, when if you calculate the value of the resistance between these 2 points, means the upper and the lower should be the same resistance, equally divided. Diametrically means this is semicircle, this is semicircle, the resistances are equal. The effective resistance of these two, that is R net is equal to R divided by 2. Okay, first we are going to calculate the value of the R. Yes. See, the total length of the wire, which is equal to 2 pi r, that is circumference of the circle is equal to length, that is equal to 2 pi r. According to the problem, the radius is equal to 10 centimeter, which can be converted into meter, that is equal to 0.1 meter. Here 2 pi, that is the value of the r, 0.1 into 2, it is becoming 0.2 pi meter. That is the length of the wire over. How much is length? This much of length. I want to calculate the total resistance of the wire, that is equal to, they were given 12 ohm per meter, that is resistance per unit length, multiply by the length, that is 12 into the length is equal to 0.2 pi, which give rise to 2.4 pi ohm. That is for entire circle we have this one, but we want the resistance of the half, that is semicircle. Resistance of the semicircle is equal to the total resistance divided by 2, total resistance divided by 2, because these are identical semicircle, that is 2.4 pi divided by 2, which is equal to 1.2 pi ohm. Okay, we getting this is equal to 1.2 pi and this is also equal to 1.2 pi. These two are identical. These two are identical. When the resistors are identical, we can use R net is equal to R by N. So R value is this. How many resistors are there? 1, 2 divided by 2. We get 0.6 pi ohm. Therefore, the correct option is A. This is the correct option for this problem. Yes, in the circuit shown, the value of each resistor is R. They were not providing the value of the resistor, they were given the R. Then the equivalent resistance in the circuit between the points A and B will be option A 4R by 3 ohm, option B 3R by 2 ohm, option C R by 3 ohm, option D 8R by 7 ohm. Here the missing of the unit. Okay. This problem is very simple, very simple. There are 3 different ways to solve this problem. Okay, see, for this I will draw one line at the middle of the circuit like this. This is assuming that this is a mirror. Maneli mirror ankoli. Okay, see, this is object, this is a mirror. Okay, the object image will be formed back of the mirror. It means that whatever I have taken the dotted line which resembles in the mirror, identical. This is called mirror symmetry. That is called what? Mirror symmetry. Then you are going to consider only this portion. After calculating this portion, then you are going to calculate the addition of these two. Because this and this are identical, then whatever the value getting for this, you multiply by 2. We are getting the resistance between A and B. Okay. Now, I would like to rearrange the diagram like this. Okay. This is the resistor, okay, this is A and this is C, and this is the resistor R, This is the point. Okay, I will give the points A, B, C. This is D and this is E. This is the point D. Okay, this is the resistor. This circle is over R. See here, resistance will divide equally, that is becoming R by 2. R by 2. Okay. Now the resistance between D and C, they are parallel. R and R by 2 are in parallel. You are going to calculate the parallel value of the parallel combination, that is like this. Rp1 is equal to R into R by 2 divided by R plus R by 2. If you made the simplification, you will get the value of R by 3. It means that the effective resistance of these two is equal to R by 3 ohm. Okay. This is R and this is R by 3. They are in series. This is R and this is R by 2 series, and we have this R like this. This is A and this is C. Okay. Now R plus R by 2 are in series. We are going to add these two together. We get, so R by 3, R plus R by 3. It is finally we are getting 4R by 3 effective resistance. 4R by 3 parallel with R. Now I will go for the here. This is 4R by 3. Okay. This is R. This is R. Now we are going to calculate the effective resistance. 4R by 3 into R divided by 4R by 3 plus R. Okay, like this. This is equal to 4R square by 3 followed by 7R divided by 3. Okay, this 3 cancel, this square, this one cancel. The effective resistance we are getting is equal to 4R divided by 7. 4R divided by 7. Okay, this is we are getting half. This much we are getting. The effective resistance between RAC is equal to 4R divided by 7. Similarly, the resistance between CB is also same, 4R divided by 7. Then they are in series. You are going to add. Add means multiply by 2. We get the effective resistance is equal to that is RAB, which is equal to this plus this. If you add these two, we get 8R divided by 7. So this is a lengthy problem. Okay. The correct option for this question is D. Next question number 19. The resistivity of iron is 1 into 10 raised to minus 7 ohm meter. The resistance of the iron wire of particular length and area is 1 ohm. If the length and diameter of the both are doubled, then the resistivity in ohm meter will be option A 1 10 raised to minus 7, option B 2 10 raised to minus 7, option C 4 into 10 raised to minus 7, option D 8 into 10 raised to minus 7. See, one must know the concept. See, we have a equation R is equal to rho L by A. In this concept, resistance they may depends on length, area, temperature and the material, but the resistivity it does not depends on the dimension. This is a proportionality constant, and it is only depends on the factor that is called temperature and the material, which material we are using. Okay, only depends on these two. If suppose you are changing the diameter or increasing the length or decreasing the area, whatever it may be, resistivity of the material does not change. So resistivity does not depends upon the dimensions of the wire. Therefore, resistivity remains the same. Hence, the correct answer is first one, 1 into 10 raised to minus 7. Question number 20. Two metal wires of identical dimensions are connected in series. If sigma 1 and sigma 2 are the conductivities of the material wires respectively, the effective resistance of conductivity of the wire of the combination is option A sigma 1 plus sigma 2 divided by 2 sigma 1 sigma 2, option B sigma 1 plus sigma 2 divided by sigma 1 into sigma 2, option 3 sigma 1 sigma 2 divided by sigma 1 plus sigma 2, option D 2 sigma 1 sigma 2 divided by sigma 1 plus sigma 2. Okay. The solution for this, okay. See, see, we are going to connect the two identical metals. So, this is R is equal to R1 plus R2, that is series combination. Okay. See, for series combination like this, you are going to have like this. Okay. Two identical. The area of these two is the same area. Okay. The length of this I would like to take L, because length is also same LL like this, but conductivity of this and conductivity of this is different. Okay. See, we have a basic formula, R is equal to rho L divided by A. R you can write, this is equal to sigma A. This is resistivity. Reciprocal of resistivity is conductivity. Okay. By taking the help of this equation, we can write for total resistance is equal to 2L by sigma A. Why I am taking 2L? The total length is L and L, it is becoming 2L. Sigma is the total effective conductivity sigma, and area is same for the two, therefore A is equal to R1 can be written as L divided by sigma 1 into A, because length are same LL, plus R2 value is L divided by sigma 2 into A. Here length is same, identical, area is same, take it common and cancel each other, we get 2 divided by sigma, 1 divided by sigma 1 plus 1 divided by sigma 2. Okay. Now, by taking the doing this simplification, you are going to have sigma 1 by sigma 1, 1 by sigma 2. Okay. That is sigma 1 sigma 2, sigma 1 plus sigma 2, that is 2 divided by sigma. We want value of the sigma. Sigma is equal to 2 sigma 1 sigma 2 divided by sigma 1 plus sigma 2. So, therefore, for the given problem, the correct option is D. So, this is the correct option. Question number 21. Identical piece of germanium and copper are taken and cool them. Option A, resistivity of both increases. B, resistivity of both decreases. C, resistivity of copper increases and germanium decreases. Resistivity of copper decreases and germanium increases. Okay. First we know the basic concept. See, already we discussed about the variation of resistance with temperature for case of metals, alloys and semiconductor I have discussed. Metals and alloys, they were change means that temperature increases, resistivity also increases. But in case of semiconductor, when we increase the temperature, resistivity decreases. Taking the help of this graph, for metals we have resistivity versus temperature. If temperature increases, resistivity also increases. In case of semiconductor, resistivity decreases with increase in temperature. But the problem they were given, two identical pieces they are taken, cooled means they are going to reduce the temperature. They are going to reduce the temperature. If you reduce the temperature like this, both the cases, in this case, okay, resistivity decreases. In this case, resistivity increases. For metal, decreases. For semiconductor, increases. Therefore, the correct option is D. Resistivity of copper decreases and for germanium, it is increases. Question number 22nd. 13 resistors, each of resistance R ohm, connected in this circuit as shown in the figure. The effective resistance between A and B is option A 2R ohm, option B 4R by 3 ohm, option 3 2R by 3 ohm and D R ohm. See, when we observe this figure, it is very complicated when we observe, but once we know the how we are going to solve, then it is become very easy. Okay. See, here this look like a Wheatstone bridge. I will take, this is the whole thing, it is becoming P, and this is the whole thing becoming Q, and this is the whole thing becoming R, and this is the whole thing becoming S. Okay. You observe the same connection over here, same connection over here. Okay. It means that whatever the effective resistance getting on this, no, this are identical. When all the resistances are identical in a four arms of the meter bridge, then this bridge is sensitive and sensitive. Therefore, the equivalent resistance is equal to any one of them. either P, R, Q, RS or S. Okay, any one of them equivalent resistance is same. Okay, now it means that the potential at this point and potential at this point is same. The current through this resistor is 0. While you are taking, you are ignoring this resistor. You are not supposed to take 1. These two are in parallel. These two are in parallel. R and R are in parallel. Okay, this is becoming 2R. These 2R and R in parallel. Sorry. Yes. See, these two are in series. It is effective resistance is 2R. This 2R is parallel with the R. Calculate the value of the resistance. That is Rp is equal to R into 2R divided by R plus 2R. This is becoming 2R square divided by 3R. R gets cancelled. This is equal to 2R divided by 3. See, all the resistors, this is equal to 2R by 3. 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 See, all the arms of this is the resistance is same. Then the equivalent resistance of this combination, which is equal to any one of the resistance. Any one of the resistance. Okay, that is 2R divided by 3 is the correct option. Correct option. Or else you can also follow the effective resistance. This is series and this is in series, effective resistance. This will take a long step. I will show that step also. Okay. This is the effective resistance calculated, that is 2 divided by R. Then the final answer is 2R divided by 3 ohm. The correct answer is equal to C. Question number 23. The resistance of the conductor is at 100 degree Celsius and 0 degree Celsius are 8 ohm and 4 ohm respectively. The temperature coefficient of resistance of the material is option A 0.04 per degree Celsius, B 0.08 degree Celsius per degree Celsius, option C 0.001 per degree Celsius, option D 0.01 per degree Celsius. See, we have a formula, variation of resistance with temperature. This is the formula. For this variation, we are going to have an equation like this. This is resistance and this is temperature. This variation which is given by this equation. Rearranging this equation, we get alpha is equal to R minus R naught divided by R naught into T. This can also be taken as RT, that is resistance at temperature. Okay, here the value of resistance is 100 degree, that is equal to 8 ohm. When it is in 0 degree, it is equal to 4 ohm. R naught is equal to 4 and the temperature is equal to 100 ohm. 8 minus 4 is equal to 4. 4 into 100 is equal to 400. This is 1 time and this is 100 time, which give rise to 1 divided by 100. 1 divided by 100 can be written as like this, 1 into 10 raised to minus 2. If you substitute if you shift the powers, we get 0.01 per degree Celsius. The correct option is equal to D. D is the correct option. Question number 24. Which arrangement of 4 identical resistors should be used to draw maximum energy from a cell of voltage V? They were given 4 options. A 2 parallel, B 4 are parallel, C all are in series, D 3 are in series, 3 are in parallel, 1 is in series with the combination. Okay, they were given the problem like this. The maximum energy from a cell of voltage V. Maximum energy means there is a condition. For maximum energy, the equivalent resistance of the combination should be the minimum. See, among the 4 combination, in which combination we are getting the effective resistance is minimum is, see here we are getting R by 2, okay, this is equivalent is equal to R by 2 plus R by 2, we are getting more, this amount. This is equal to identical R by 4. This is equal to 4R. This is equal to 3 R by 3 plus R. Among these 1, 2, 3, 4, Okay, this is the lower value of the resistors. When all the resistors are connected in parallel, effective resistance is low. So therefore, this is the correct option, because the condition itself is maximum energy, the equivalent resistance of the combination should be minimum. So therefore, the correct option is B. All the resistors are connected in parallel. Question number 25. 5 equal resistors when connected in series, the power dissipated is 5 watt. If they are connected in parallel, the power dissipated will be A 25 watt, B 50 watt, C 100 watt and D 125 watt. Okay. See, I would like to first consider that the series combination. 5 equal resistors, the effective resistance is equal to RS is equal to 5R, because identical, all are identical. Therefore, this is the power in this combination is equal to 5 watt. Therefore, by using the formula P is equal to V square divided by R, substitute the values. Okay, P is 5 and RS is equal to 5R. Substitute the values. Okay, this 5 shifted over here. 5 into 5, it is becoming 25. That is V square by R is equal to 25. Give it as equation number 1 over. Now, the same resistors in parallel, then the effective resistance is R by 5. We are going to calculate the what is the power in this combination. That is P dash is equal to V square divided by R net. You are going to calculate the P dash, that is R net is R by 5, substitute. 5 is shifted to up, it is 5 V square divided by R. V square by R is equal to how much? 25. Substitute V square by R is equal to 25 in this equation. 25 into 5, which gives rise to 125. Therefore, for this correct option is equal to D 125 watt. Question number 26. 3 electrical bulbs of 400 watt, 200 watt and 200 watt are shown in the figure. The resultant power of the combination is, okay. See, C and B are in parallel and A is series with this parallel combination. First we know the options. Option A 800 watt, option B 500 watt, option C 200 watt, option D 600 watt. Okay. For parallel combination, we have power in parallel is equal to P1 plus P2. For this particular problem, PC plus PB. You can take PC plus PB. So this is 200 plus 200, which is equal to 400 watt. Okay. This 400 watt is in series with the 400 watt bulb. Both are in series, like this. This is, okay, this is the combination, that is a parallel PP, parallel combination, how much? 400, okay, this is 400. When they are in series, we have effective power in series is equal to 1 by PS is equal to 1 by P1 plus 1 by P2. Okay, if you using this formula, we can calculate like this, that is P total is equal to P parallel, that is P1, that is PA. Okay, by taking the help of this 400 into 400 divided by 800, okay, these two zeros are cancelled. 4 into 400 is 1600 divided by 8, or else you can simplify, this is 1za and this is 2za. That is 400 divided by 2, which is equal to 200 watt. Therefore, the correct option is equal to 200 watt. Question number 27. Question number 27. 2 bulbs X and Y having the same voltage rating and the power 40 watt and 60 watt respectively are connected in series across a potential difference of 300 volt. Then A, X will be go brighter, Y will glow brighter, and C, resistance of Y is greater, and D, both will glow equal bright. See, the concept is very simple. When the bulbs are connected in series, okay, the lower wattage bulb will go more brighter. That is a concept. So therefore, this is the X1, the lower wattage, that is equal to 40. This is 60. Therefore, this value is 40 watt. This is X. Therefore, X will glow brighter. So therefore, the correct option for this is equal to A. Okay, when they are connected in series, lower wattage bulbs are glow more brighter than the higher voltage. Yes, question number 28. A cell of EMF E connected with an external resistance R and a potential difference across V is V, across the cell is V. The internal resistance of the cell will be A EVR divided by E, B EVR divided by V, option C E minus V divided E minus VR divided by V, and D E minus V divided by R divided by E. Okay. See, we have a basic formula, okay, that is V is equal to E minus IR. If you shift IR over here, it is becoming E minus V. Therefore, R is equal to EV divided by I. But we know that from Ohm's law, I is equal to V by R. In place of I, you are going to substitute V by R. R will go up. It is becoming E minus V into R whole divided by V. Therefore, the correct option is B. This is the correct option. Question number 29. A battery consists of a variable number N of identical cells, each having an internal resistance are connected in series. Full stop. The terminals of the battery are short circuited. The graph I in the circuit versus the number of cells as shown in the following graphs. See, option A, that is parallel to the x-axis, that is a number of batteries, and option B decreases, option 3 increases, option D also linearly increases. But we have I is equal to NE divided by R plus NR. This is the current expression when number of cells are connected in series, where NE is the effective EMF and NR is the effective internal resistance and R is the external resistance. See, short circuited means the capital value R value is equal to 0. If you substitute the value of R is equal to 0, then we get I is equal to E divided by N. So, current is equal to E divided by R. It means that there is no N term in this equation. It means that current does not depend on the number of batteries. Current does not depend on the value of the N. So, therefore, we get a curve like this. If you plot current and the number of batteries like this, we get a straight line. Therefore, the correct option for this is equal to B. Correct option is equal to B. Question number 30. 12 cells each having the same EMF are connected in series to form a battery. In this battery, some of the cells are wrongly connected. When this battery is connected in conjugate with the two more identical cells in series, the current in the circuit is 3 ampere. When the battery and the cells are connected oppositely, then the current in the circuit is 2 ampere. How many cells in the battery are wrongly connected? Option A 1, option B 2, option C 3, option D 4. See, this is the expression for I is equal to NE divided by NR. See, when there is no external resistance, it is short circuited, we have an expression I is equal to NE divided by NR. Okay. For wrong connection, how you are going to calculate the total EMF? That is E is equal to N minus 2x into E. Here N is the number of cells and X is the wrong connected cells. E is the EMF of each cell. Okay. By taking the help of the first equation, the first case the current is 3 ampere. The total number of cells to form a battery. See, this is a battery, they were connected by 12 cells. This is the battery. Okay. That is 12 cells. These two are the wrong connected cells into E. For this combination, 2 more cells are connected in series. 2 more cells are identical, E and E. Therefore, the effective EMF is equal to 2E. Therefore, total 12 plus 2. How many internal resistance? How much internal resistance? This is 12R, this is 2R. Total it is becoming 14R. Okay, this is equation number 1. Similarly, the connection for this battery, this is 12 cell battery. The connection is wrong connected like this. Wrong connected. Cell, this is positive, again like this. this is E, this is E. Okay. Now we are going to have the equation like this. Okay, wrongly connected means same connection, wrongly connected, which is negative terminal, this is negative terminal, like this, wrongly connected. Then the effective equation is this, because current in this case is equal to 2 ampere, that is 12 minus 2x E minus 2E divided by 12 R. Total cells is equal to this much. When we divide these two, it is becoming 3 by 2, and the E terms is cancelled on the both side. 14R cancelled. So remaining is 3 by 2 is equal to 14 minus 2x divided by 10 minus 2x. By made all the simplification, we get the value of the x. We get the value of the x is equal to 1 mole. The wrong connected cell is only 1. Therefore, the correct option is first one. Question number 31. Question number 31. Question number 31. There are 72 identical cells, each of EMF 2 volts and internal resistance is 2 ohm. The resistance, the series and parallel combination which provides the maximum current through 9 ohm, the resistance is A. 6 row with each row containing the 12 cells. B. 18 rows with each of containing 9 cells. Third, C option, 4 rows with row containing 18 cells. D. 9 rows with each row containing the 8 cells. See, the condition for the maximum current in the circuit. The condition for the maximum current in the circuit is, that is, external resistance is equal to the effective internal resistance. The external resistance in the problem they were given 9 ohm, and they were given internal resistance is also equal to 2 ohm. If you substitute these two values in this equation, okay, we are getting the value of N is equal to 9m divided by 2. We know the value of M. But the total number of cells is equal to M into M. They were also providing, that is equal to 72. 72 is equal to Mn. Then substitute the value of N in the equation. Okay, like this. We get 1, because cross multiplication, 72 into 2 is 144. This 9 is shifted over here. 144 divided by 9 is equal to M square. Therefore, M is equal to 12 divided by 3, that is equal to 4. Therefore, M is 4 and N is equal to 8. It means that N number of cells are connected in series in M row. Hence, the correct answer is C. Thank you.
ಆಯ್ತು ಗುರು 5 ನಿಮಿಷ ಎಕ್ಸ್ಟ್ರಾ ಆಗಿದೆ.